Hello, everyone. Good morning, good evening, and good afternoon. Today, we are into a webinar which is co-hosted by ACL Digital and Phoenix AI, which is primarily focused on AI-powered anti-jamming technologies, which helps the enhancing the drone security. So the primary interest would be to talk about, what are the current drone security related challenges and how it is being and kind of, gone through or covered up with the AI powered technology that Phoenix AI and ACL Digital is kind of bringing it up in this webinar session today. So as part of this webinar, our agenda is kind of primarily split it into specific sections. The first part would be to introduce about the team behind this webinar and this solution, and to talk about the current jamming solutions, which is of the primary interest, and how Phoenix AI's anti-jamming solutions is important for ACL Digital, and also, the current industry is going to be the focus. Then the focus would be to talk about the solution and the demo around that. And last few slides will be to talk about the company overview of Phoenix AI along with ACL introduction. We have kept a Q&A session to kind of bring up any questions that you have, and we will be happy to address that over the session. So today's presenters were there in the call. Dr. Craig, who's the co-founder and head of engineering and VP for the Phoenix AI. We also have Rajesh Rasalkar, the co-founder and CEO of Phoenix AI. And the other speaker would be Dr. Vignesh Manohar, who is the co-founder and CTO for Phoenix AI. And myself, Arunesh, I head the sales and business development for ACL. With this, I'll hand over the next sessions to the Phoenix AI team.
Morning, good afternoon, good evening, everyone. Today we are going to deep dive into the crucial topic of drone and GPS jamming and anti-jamming technologies. And with the increasing reliance on the drones for various applications, the protecting them from jamming attack is more important than ever. Additionally, GPS systems are integral to numerous applications for drone. Protecting them from jamming attack is essential. So let's explore what the drone and GPS jamming and anti-jamming is and how it works and its importance. Okay. So what exactly is the drone and GPS jamming? So simply put, a drone jamming is the process of disrupting the communication between a drone and its controller. That you can see it in the slide. So this is achieved by like emitting a radio frequency signal that interfere with the drone's communication links. Effectively, it to receive a command or transmit data between the drone and the ground station or the remote power, I'll say pilot here in this case. At the same time, the GPS jamming is similar. The GPS jamming is a deliberate interference with the signal from GPS satellite, preventing the GPS receiver on the drone from determining their locations. Again, this is achieved by like transmit a signal on same frequency as GPS satellites, thereby overpowering the legitimate signal that's supposed to be coming to the GPS. And if someone is successful in jamming both these things, you basically effectively make the drone non-operative or make it crash. So you can imagine the protecting a drone from jamming is going to be a super crucial. So if you want to go to the next slide, I think we can talk about some of the existing solutions here. As jamming is very important, but I think there are some issues with the current existing solution. So in this case, anti-jamming refers here the techniques or technology that used to protect the drone from this signal interference or jamming attacks. While the current anti-jamming technologies are effective, but there are challenges and opportunities for improvement. And current existing anti-jamming solutions, they are mostly hardware-based. Again, it doesn't scale well. It's not effective. As you can imagine, the technologies are moving fast. Especially in the now the with wars going on, the drones are becoming essential parts of the war. So I think you can imagine with increased, I'll say, funding and a lot of things going on with jamming, there is a lot of development happening where having the effective anti-jamming solution is very important. In addition, again, jamming technology is also advancing, correct? So continuous innovation is very essential. The future direction is very clear to use the AI, the power of AI to predict, counterattack the jamming attempts in real time. And that is why Phoenix has already developed some solutions. So why effective solution is important here, correct? So drones are increasingly used in critical operations such as military missions, disaster response, commercial deliveries, infrastructure inspections. So jamming attacks can compromise these operations, leading to a mission failure, security breaches, or even accidents. So drone technologies have similar, like very, have several critical applications like military defense, ensuring the secure, reliable operation in hostile environments, emergency services, maintaining control of drone used in disaster response and search and rescue missions, commercial use, protecting the delivery drones or industrial inspection drones from interference, public safety, ensuring the drones used for public safety and security are not compromised. Each of these application underscores the importance of robust anti-jamming measures here. Uh, I think I'm going to play a short video about actually our technology in actions. Uh, and I'll tell you why it is important that we are playing this video.
Their missions doomed to fail. Drone jamming and GPS spoofing. A dual threat to modern warfare. Communication is severed, navigation compromised. A critical mission hangs in the balance. Without communication or navigation, drones become liabilities, lost in the sky, their missions doomed to fail. But what if drones could outsmart jammers and spoofers? Phoenix AI's AI Navigator software makes it possible. Our cutting-edge reinforcement learning technology empowers drones to adapt to their environment in real time. Like a chess grandmaster, the AI anticipates the adversary's moves, safeguarding communication, navigation, and ultimately, mission success. Phoenix AI's solution isn't just about anti-jamming or anti-spoofing, it's about mission assurance. Protecting your assets, your personnel, and ensuring your tactical advantage. Get Phoenix AI-enabled anti-jamming software on your drone and complete your mission.
Thank you, Craig. Just wanted to reiterate here, we will have a demo about our software platform, but just wanted to say like it's illegal activity to use jamming outside. So yeah, please don't use jamming outside. There are FCC mandates. You may basically interfere with the other radio frequencies, and there might be some legal issues. So that is why I think what we are going to show, what we are seeing in the video, but we'll show in more in the demo in simulation platform. And our simulation platform is very flexible in terms of capabilities. So now I'm going to hand over the floor to Dr. Vignesh Manohar, who is the CTO of Phoenix AI, and Dr. Craig Kleski, who is the head of R&D, to discuss our technology and provide a short video or the demo about our technology.
Yeah, thank you, Rajesh. I hope I'm audible to everybody. So just like Rajesh said, we at Phoenix AI are looking to develop a very intelligent middleware, and the aim is to equip the drone with the intelligence to always stay in regions of good connectivity, right? And this actually includes, to be in regions that are free from jammers. So this slide actually shows the big picture of our algorithm and the big vision that we have within Phoenix AI. So as you can see, our goal is to process multitude of data that comes from camera, LiDAR, radar, GPS, etc. Process this through a very intelligently enabled, machine learning RL kind of network that we develop in-house. And through this RL network, the outputs of this would be a model-based predictive path, model analytics, heat map, etc. So finally, we are using this AI and RL algorithm to inform the autopilot so that it makes good decisions to always keep the drone in spots of good connectivity. And I would like to emphasize here that just because we optimize connectivity, it doesn't mean that we lose track of distance or we lose track of the fact that the drone has to reach the destination. So our algorithm is very intelligently coded so that no matter what happens, the drone will always reach its destination. So one of the major advantages for our algorithms, it includes, the software working on a multitude of hardware platforms, because the way we do it, all the training is accomplished offline. And so the drone only carries a lookup table with it as it flies, which allows it to always take good decisions while in flight. So this makes it extremely customizable. So if you have a drone, a very simple DJI drone, we can give you a code that will work with that platform. Or if you have a very advanced drone with very advanced computing capabilities, we'll organize our code, to serve your needs with that platform. It's very cost effective because it completely lives on the software layer. So we don't need any major hardware enhancements on the drone just so that it flies in regions of good connectivity. It's extremely scalable. And also we are communication modality independent. So which means, whether it's satellite, Wi-Fi, cellular, it doesn't matter to us because we really don't go beyond the signal to interference ratio for the network. Yeah, next slide, correct. So now this was the big picture, and now we kind of boil it down to this webinar where we focus on the anti-jamming portion of our algorithm, right? And so for this, at least for the purposes of this webinar, I assume that the drone is actually being connected to the internet via the cellular backend, right? So it's connecting to cellular base stations, and then there's a jammer that is standing and trying to jam the cellular signal. So to this end, we take inputs such as base station sectorization, base station antennas, patterns, scheduling, etc. All that we plug into an RF simulator that we have designed in-house, and this gives us a certain heat map. Then this heat map is used to train our RL algorithm, and finally, you can see a representative output in the figure below, where we have the green path, which is the distance minimized route. So that's just a straight path from A to B. And then you have the yellow path, which is actually the SINR optimized route. And you can clearly see that in this one, the drone is striving to maximize its time that it spends in the red regions, which is the regions of good connectivity. And it minimizes the time that it spends in the blue regions, which are actually zones of poor connectivity. This is just a representative result. And in the next slide, we'll show results which are more particular to jamming. So here, let's start with figure 1. So in the background of figure 1, you can see a heat map. And this heat map actually assumes a grid of 3 by 3 base stations. So it's just 9 base stations. All of them are radiating at 2.5 gigahertz, right? And the heat map we synthesize and we give it to the drone to fly and to learn this full heat map so that it always stays in regions of good connectivity. Now, first, I would like to draw your attention that there are two paths here. One is the red dotted path, other is the black solid path. The red dotted path is actually the path that the drone would take if we only let it maximize the signal quality, right? So it doesn't know of the jammers, right? Whereas the black solid path is the path that the drone now takes when the jammer is actually there on this optimized path. Now, I would like to stress on this point that the training has never seen the jammer. It's only during evaluation when the drone is really flying in real life that the jammer is present. So the drone is making its decisions completely real time during flight in the presence of a jammer. So first you can see the drone flies on a path which is equivalent to the path without the jammer until it hits jammer A. Once it hits jammer A, I would like to draw your attention to figure 2, which is on the right top portion of the screen. And you can see that the red path actually flies right through the jammer because the red path didn't know of a jammer before. And now you can see in comparison the black path intelligently avoids the jammer. So you can see it totally avoids the main beam of the jammer antenna, and it decides to fly only via the side lobes and the nulls that is present in the jammer antenna pattern. And we know that the side lobes and the nulls actually provide much lesser interference than the main beam of the jammer antenna. So you can see it successfully skirted jammer A, and then it actually tries to come back to the pre-planned route, which is the red dotted. However, there's another jammer B, which is placed very close to jammer A. And so it senses that, and you can see, even though the path is now pretty close to the pre-planned path, it's trying to avoid jammer B, and this combination of the jammer B being very near jammer A and the RL algorithm striving to avoid jammers, you can see that jammer B is totally avoided in this case, right? And then once jammer B is passed, you can see from figure 1 that the paths again merge and the drone has come back to the pre-planned path. And then after a certain distance, we come to jammer C, right, which is now figure 3. And here you can see that the actions that it takes for the jammer C is very similar to jammer A, in the sense it's still able to totally avoid the main beam of the jammer and only fly through the nulls and the side lobes of the jammer. So this is actually a very interesting result and a very interesting capability. And I would again like to re-emphasize here that all of this is happening in flight real time. Like, we haven't pre-programmed any jammer locations. So during flying itself, the drone senses that it's going to a jammer, and it does its best to avoid it in real time. And also, I would like to again re-emphasize that only minimal deviations are seen when there is a jammer, and this is actually can be really important for mission critical, for very sensitive missions, where the path itself is very sensitively planned because it's a strategic mission. So this is a representative result where our algorithm is avoiding jammers, and we have a pretty interesting result on the next slide, where here you can see on the figure on the left, we've actually taken the center base station out to create a dead zone right in the center of the heat map. Now, what I would like to emphasize here again is that even though we created this null zone by taking a center base station out, in principle, that null zone could also be, an omnidirectional jammer that is creating a jamming cone or a certain geofencing, right, where the drone cannot enter a wide area. So it can either be created due to user traffic, or it can be created due to a lot of jammers or a conical jammer present in that area. Again, the training that the drone has seen is actually the heat map that you saw previously in the previous slide. So that has all the 9 base stations, and everything is good. So here you can see point number 1 is that the straight path from A to B, which is the solid blue path, flies right through the zone of bad connectivity. So we don't want that. In contrast, now if you see the black paths, right, the black paths totally avoid the center zone, which is the zone of low connectivity. And now as it flies, I again introduce a spot jammer, right, in the top portion of the path. And now you can see that the black dotted one is the path that the drone would have taken if the jammer was not present. And then the black solid one is the path that the drone now takes once the jammer is present. And again, you can see it's able to skirt this jammer as well and come back to the pre-planned route, right? So in summary, our algorithm is very well equipped to take care of multiple aspects. We are optimizing wireless connectivity. We are avoiding spot jammers, which can just be a very focused gun that somebody has on the ground. And we are also avoiding zones of omnidirectional jammers, which can jam, a wide area and inhibit drone operations within that area. And with this, I'll wind up the technical deep dive into our code, and I'll hand over to Craig to do a demo of this on hardware. Before I do that, I would also like to emphasize that you guys can actually put your questions on the chat as well, and we can respond as we go. So please feel free to put all your great questions in the chat. Yeah, over to you, Craig.
All right, thanks for that, Vignesh. Those are cool results. All right, so I'm going to show some of the results that Vignesh presented in our simulation platform. But let me talk about a little bit how our simulator works and how our software would work when actually deployed on the drone. So what I'm going to talk about is what's called offboard control with ROS. So ROS is robot operating system. So this is a popular SDK for interacting with drones or actually interacting with all kinds of other robots. And basically what ROS is it's a way of facilitating message passing between various processes. So you can think these are processes, say, running on a single computer, or these could be processes running on completely different computers that have some kind of communication link between them. So you can imagine one of these processes is the drone, and the second process is some computer, say, that's controlling the drone or giving the drone some commands. So in our case, what we're looking at is the drone is going to be sending messages from its various sensors. So depending on the capability of the drone, it could have very complex sensors. But what I'm showing here is just kind of a minimal example where the sensors that it might be reading from are just the IMU. So it's giving all the information about the state of the drone, including, for example, say its GPS location, if that should be available. Also, we want to know something about the link quality. So basically the RF heat maps that Vignesh was showing before, which we want to know, like at the moment where the drone is in this location, what is the link quality. So the outputs of these sensors are communicated via these so-called ROS messages, and they're sent into our software. So our software could be running off-board. Like I said, there could be a communication link between the drone and some remote computer, or the software could be running on the drone itself. And so then our software is going to be taking in these various sensors and processing it and coming up with commands that would be sent back to the autopilot for the drone to execute in that moment. So these messages, they're passed with at regular intervals. They're passed with regular intervals from the drone at a certain frequency or a certain hertz, and then commands are passed back to the drone at regular intervals as well to update the drone's position, its velocity, etc. So the inputs, the kind of the basic inputs then into the simulator and to the deployed system are a drone that has the PX4 autopilot. This is very common on drones, and just the way that we can read off its sensors for using our algorithm. Okay, so now we're going to show a little piece of what Vignesh was showing before about how the drone responds when we put a jammer directly into its path. So what we have done here, we're going to show a simulation of how the drone will move in reaction to this jammer. And we're using a software platform here called Gazebo. So Gazebo is often paired with ROS, and it's a way of really verifying that what you're doing is going to have some fidelity to real life. So Gazebo provides the physics, and it provides the interaction with the PX4 autopilot. So again, the point of this simulation is when we run this and we see good results here, we can be pretty sure that if we deploy this in the field, that's the result that we're going to see. And going back to something that Rajesh said before, we can't just take a jammer out into the real world and test the software. So we have to do it in simulation first. Okay, so the scenario that we're going to present, again, we're going to see what happens when the drone, who has never seen this particular flight with a jammer, we're going to throw a jammer in the middle of the route and see what it does. Okay, so I'll pause here just to tell you what's going on. So you just saw in the background this sequence of green spheres rising from the ground. That's the drone. The drone's taking off. And it's about to go on a path that's approaching this big black sphere here. So this big black sphere represents the jammer. So obviously this is a simplification of the beam of the jammer itself. All right, and now the drone is starting to move. In real time, it's taking in input from its sensors and it's making decisions in real time about how to move. So it's responding to the RF heat map basically and making most of its decisions. So it's getting closer to the jammed region, which is intentional. We put the jammer directly in the way and we want to see how it's going to respond. So as it gets closer to this jammed region, it's going to start making decisions to avoid this jammed region as it senses that the signal quality is getting poor. So you see, I'll just pause for a second, making small deviations away from this jammed region. Again, as it's detecting the signal quality is getting really bad. So it continues to skirt this jammed region. And in fact, it completely avoids the main beam of the jammer. And now we have it landing here Okay, so on this very short mission, the point again was the following. During training, this drone had never seen this region of jamming at all. In fact, it went directly through the jammed region, and then we intentionally jammed, and it's successfully able to skirt this jammer. Okay, let me just tell you a little bit about the software requirements for us. So we're imagining our software, we want to have software that is able to work with existing ecosystems. For example, if the customer already has various sensors or algorithms on board, we want to be able to work within that structure. What we're designing for is for fairly lightweight processing. So all of the training for the algorithm itself takes place entirely off board, not on the drone. I mentioned this before in the context of ROS, but the software can be run either on the drone itself, or it could be run off board via some kind of communication link to some computer. So we'll have different versions of our software depending on different use cases for customers. Again, depending on the customer's current ecosystem, we want to be able to work with that ecosystem. But you can also imagine we want to adapt to the requirements that are present on the drone itself. So if we have a drone with minimal compute power, minimal sensor configuration, we have configurations of this that will work with that kind of platform. If it's some kind of very simple DJI drone, for example, we have a configuration that works with that. If we have a more advanced drone, like we have this Sentinel drone pictured here, in this picture, if we have a more advanced drone with GPUs, various other sensors, LiDAR, radar, whatever, you can imagine we have a more advanced configuration that can take more of these inputs and at the same time have better capabilities, better performance. Okay, and with that, I will hand things back to Rajesh.
Yeah, thank you, Craig. I think this was an excellent demo. I think there are multiple demos that we have done. I think a lot of simulations. I think what we have shown is mostly on the RF jamming for signal jamming, but I think similar, basically you can see the GPX jamming. It's a similar software function, the machine learning code, but it uses the GPS signal basically to monitor, and it avoids the GPS jamming as well. Happy to take any questions. Maybe we'll quickly talk about what we do exactly at Phoenix. So we are on a mission to develop an advanced AI navigator to achieve like true level 5 autonomy for any vehicles flying in the sky, such as drone, which are also called unmanned aerial vehicles. It could be air taxis. So it could be any IoT device. Anti-jamming is just one of the problems that we are trying to solve here for safe flight. But we have other problems to solve as well for safe navigation. So go to next slide. As you can see, there are a number of use cases of what drone can deliver, package delivery, for surveillance, for remote inspections. But there are numerous challenges in terms of making the drone to fly safely. There are regulatory challenges. There are safety challenges. Such as like your drone is not supposed to fly over a heavily congested area. We have obstacle avoidance, like you need to avoid obstacles, which could be a static, it could be a mobile obstacles. The other challenge is the connectivity. Like most of the use case are happening beyond visual of line of sight, where there is no operator control. Your basically drone is flying hundreds or maybe 200 miles away. I think for that you need to have a reliable connectivity, and you can imagine, correct, the connectivity is always it's always unreliable, but our software makes this reliable, connectivity reliable. It could be 4G, 5G, satellite, Wi-Fi. Signal jamming, I think that is happening now actually. So it's a real problem that we are already solving that problem now. So go to our next slide. Okay, so in the context of drones, so level 5 represent a full autonomy, correct? So where the drone can operate without any human interventions or operator control. And this level of autonomy involves like advanced AI, machine learning, training algorithms that enable the drone to navigate, make decisions, or execute missions independently based on real-time input, which could be wireless connectivity input. It could be sensor data, and or it could be a pre-programmed algorithms, correct, or flight path. We see like the number of players are in this market who are coming from aerospace and hardware background that uses mostly a traditional method to solve similar problems. And but there are potential differences in how we are building our AI model compared to theirs. So in contrast to like classical any UAV auto navigation companies, which takes multiple sensor inputs, here we are building an underlying ML infrastructure or operating system middleware stack that consists of single large AI models that combines like route planning, input from various sensors like such as LiDAR, radar, camera, as Craig mentioned, which are very important for uh, detect and avoid for obstacle avoidance. We can take input from modems like from RF, could be 4G, 5G, satellite, Wi-Fi. It could be GPS input, or it could be a weather, correct? So I think because weather could be dynamics, and we want to make sure that the drone avoids the bad weather or it's going through bad weather. And then also there are some operator input based on use case. Some use case requires a drone to fly A to B uh, without having high throughput requirements like for classical delivery use case. In some case, use case is such as surveillance where you need to do a video feed, constant video feed. So there are different operator input that needs to be fed into the full AI/ML algorithms that we are building. So again, these are again raw input that feeds into the AI, the middleware, and then basically create dynamic navigations through autopilot. So you can imagine the more data we feed into the model, the richer and more expressive the AI model becomes for its specific applications. So our model again thrives on unsupervised learning from raw, unlabeled data. So this approach is, I would say, more hardware friendly. It's simple to integrate into silicon, and it has again low compute requirement. As Craig mentions, it doesn't require like high compute like GPUs in some cases, and it runs on constant running like time and memory. So we believe like I think this approach is more agile. It's not tied to any single input, and this is required actually to solve this level 5 autonomy in the sky, and which is also called beyond visual of line of sight, which is the BVLOS. Again, AI middleware consists of again several key components for safe and secure flight. I think drone jamming, GPS jammings. I think we have discussed this problem. Again, this is just one of the problem. We have problem with the communication systems, like making the connectivity between the drone and ground station more reliable. Uh, and as you know, wireless conditions are very dynamic, like which will be 4G, 5G, like the Sunday morning wireless conditions in the air will be different on Monday morning or Monday evening based on capacity. I think there's a lot of complex things that goes into the model. And this is why our AI model is fine-tuned based on those input. There are different sensor inputs, which provides a real-time data about drone surrounding. There is weather input, and then eventually there is the flight control software. The software execute the decisions made by this AI middleware to control the drone's movements and actions. So I think this components enables the drone to navigate like in the complex environment autonomously. So let's go to next slide. So if you look at a closer, like how our AI navigator works, right? So again, I can divide this process into like three main stages, like data collections. Basically, the sensor continuously collect data from drone environments, looking at wireless input, obstacles, weather conditions, geographic informations. Then the processing, correct? The AI algorithm analyze this data in real time, and most of this AI algorithm is built on the drone because we believe like drone needs to be intelligent enough. It needs to take the path dynamically because most of the conditions are dynamic in nature. So you may able to do a pre-path between from drone to fly from A to B, because the conditions are so dynamic, I think most of the intelligence has to sit on the drone itself. So the drone needs to process this data dynamically and makes the decisions about the patterns, and also look at the prediction analysis, and then also the decision making and executions. So based on process data, the flight control software can make decisions and execute them, adjust the drone's flight as needed. So I think what we are building is more AI framework that also is useful for more for analytics functions. And like if you want to do some kind of analytic, how the drone is flying or how the drone is moving from A to B, how it avoided obstacles. I think this kind of data will be useful for drone operators or for drone insurance company, which they need to know how the safety of the drone, how it is flying. I think you can go to next slide. Okay, so our AI Navigator offers like many benefits and allow for drone operator to overcome some of the challenges. I think one is the regulatory challenges, navigating the regulated landscape to ensure the compliance with safety, privacy standards very essential. So our software is compliant to ASTM, IEEE 1920 standards. It aligns with FAA, ISA regulations and safety requirements. Then also the data privacy and security concerns. Basically protecting the data that we process on the drone is fully secured. And some of the features which requires always on connectivity, real-time obstacle avoidance, real-time RF, GPS jamming, real-time bad weather avoidance, uh, and also like the battery life and performance. So enhancing the battery technology to support longer and more and enable more complex missions. And one of the important feature about AI model is also avoiding the crowded area. So you may able to do a pre-path flight to avoid some of the areas like using geofencing and other thing. But if the crowded area is happening dynamically, if there are some events happening which are very dynamic in nature, our AI models on the drone itself can detect that the gathering happening in that place, and it can navigate the drone to avoid those. Uh, I think that's one of the important feature for safety. And uh, I think this kind of feature actually enable like I'll say highest level of autonomous operations even in complex and dynamic environments. Uh, and again, I think you can imagine, correct? So I think if you achieve like a true level 5 autonomous drone, I think it can deliver like number of applications for various industries such as delivery services, enabling the full autonomous delivery operations, improving logistics, and so reducing the delivery times. Infrastructure inspection can like conducting a detailed inspections of bridges, power lines, pipeline without human interventions is very critical. Emergency responses, quickly responding to disasters, conducting search rescue missions, and also delivering the supplies autonomously is very critical. Surveillance security, providing like continuous monitoring for large areas, detecting and responding to potential threats is very important. Agriculture is a big use case, like performing tasks like a crop monitoring, spraying, planting, uh, like with high efficiency is very critical. And the military and defense, as you can see, nowadays drones are part of the wars. I think protecting, making the drone to fly autonomously is one of the big use cases that we are targeting. So these are some of the complex topics that we are actually covering. I'm going to hand over the floor to Arunesh from ACL to talk about the ACL role in these ecosystems, and maybe then we can take any questions that you may have.
Thanks, Rajesh. This was a great presentation. And before going into the ACL part of the slides, I would want to definitely bring up one important aspects of why ACL or maybe Alton Group as a company has partnered on Phoenix AI. It was a couple of years ago where we as a company we have a lot of exposure to the aerospace and autonomous kind of solutions. basically with the customers that we work upon, we were always asked upon what is the differentiators that you carry, and is there something that you feel that the current environment related challenges that you see in the drone related ecosystem, is there something that you can bring in as a value add? And that's where, we kind of partnered with ACL Digital. Sorry, we partnered with Phoenix AI, and the solutions that kind of Phoenix had talked about was very impressive in front of our customers. Typically, the jamming avoidance and always on kind of a model where it talks to the satellite, Wi-Fi, all of that, and also the obstacle avoidance and the AI middleware software that Phoenix AI has come out has been one of the standout in couple of our discussions that we had with our customers. So we are in some of the early discussions and some are in the demo stages, and I believe that as a company, Phoenix AI has a great value in the value proposition with the offerings that they carry, and I'm looking forward to have a larger engagements with the kind of discussions that we see around. With that, I'll just touch upon, what we do as a ACL Digital as an organization. Maybe we can go to the next slide. So we are part of a group. We are nearly at a $4 billion organization and nearly around 6,500 clients with an employee strength of around 57,000 people. Primarily a French stock listed company, and we work on all the domains: automotive, aerospace, banking, finance, healthcare, retail, and defense also is one of our larger engagements. And that's where, we kind of felt that it's important to partner with, Phoenix AI. So we work with the top of Fortune 500 companies, and, it can be in all domains. And region-wise, we are spread across the entire globe, and we work in around 30 plus countries. The next slide. So ACL Digital is part of Alten Group, and ACL brings in a different value set altogether in the overall Alten value proposition. We carry more onto the high-tech side of business, and one of them is one we are just talking with Phoenix AI. But other than that, we work on the VLSI side of things. We work on the 5G. We work on the cyber security and other AI-related solutions, and primarily mostly focused on the embedded. We typically call ourselves as a chip to cloud company, only focusing on the horizontals that you see in all the verticals that I talked in the last slide. Next slide. Yeah. So this is the verticals that we work around. As I just talked about, in all of these segments, we work with the Fortune finders in that list. So we are pretty much there everywhere, and we try to bring in the solutions, the AI spoke upon, the middleware in everywhere. And we see that, as a solution, it can be enabled, it can be twisted, it real some use cases. So this is not very specific to the drone kind of a domain that you can kind of push in. But, I understand that it can be always extended to some of the important use cases that you see in all of the areas. And that's where, we feel that this solution that Phoenix AI brings in is very important for us. Next slide. So as a company, yeah, we kind of touched upon this, but as a company, we do all the way from the spec to the production and all the way to the customer management and support. We work with customers and even doing the solution engineering, solution architecture. Also, we do mostly onto the re-engineering aspect of that and complete product engineering and development services. So we have engaged customers on from the initial pilot phase, or maybe it may be in some cases where we augment their existing teams to enhance some of their existing capabilities. All the way, we kind of work in with customer in tandem, and that's where it's kind of stand out in all the segments we talked about. Next slide. So our global presence, as we spoke about, we are there everywhere. Primary focus is in Europe, but we are pretty much there even in US. We have exposure. We have in also in Southeast Asia. Next slide. So with this, I will open the floor for the questions for all of us, and we'll definitely take one by one.
I think there are a couple of questions. Maybe I can look at it. I think the first one is, so the ML is trained to take a path to maximize the strength of received GPS signal. What is GPS itself is spoofed? Maybe Vignesh, I think you answered it, but you want to maybe provide to the larger audience here?
Sure. Yeah. So that's a very good question. And so I would like to kind of highlight this fact that, we actually focused on cellular connectivity just as a representative example. In general, we can also incorporate GNSS jamming where, the drone just avoids any GPS jammer and route. And then there's a follow-up question, which is also a very good question is, what if you have a fake GPS transmitter, right? So you're spoofing GPS, so we're not quite jamming GPS. In this, regime, we will require some signal processing so that we can distinguish the signature of this spoofing, the spoofing agent, and then flag that, as a no-fly zone, and then fly from there. So that would be a more multi-step kind of approach.
Thank you, Vignesh. The next question is, what computing requirements do you need for this algorithm to work on the drone? So, Craig, do you want to add any input here?
Yeah, I can say a little bit more about this. So I mentioned it briefly before. So you can imagine what's needed depends on what the customer's need is and also what the capability of the drone is. So a very small form factor or small compute drone, as you can imagine, it's not going to have a whole lot of sensors available to it, and so its capability ultimately is going to be less than that of a more sophisticated drone with lots of compute. So the examples that I showed you in the simulation, that could be run on a drone with very little computing power. I'm talking like Raspberry Pi level computing power available. Pretty small memory requirements, pretty small compute requirements. But again, for a drone that has more sophisticated sensors and compute, we can scale this up to a more capable system that's able to take in a lot more inputs, as you would imagine, maybe that it would include a drone that has a GPU on it.
The next one is the result that you showed assumes cellular connectivity. How would it adapt to a GNSS, Wi-Fi, satellite connectivity? Vignesh, you want to take that?
Yeah, sure. So yeah, like I said, we just assume cellular connectivity because we just model the free space link between the base station and the drone and we create a certain heat map. But in general, if you have Wi-Fi GNSS, it's actually a relatively simpler problem because if we assume that Wi-Fi or GPS signals is relatively constant in the zone in which the drone is flying at any given instant of time, then the only requirement is for the drone to avoid the jammer. Wherever it goes, that'll be okay for us as long as it avoids the jammer zone. So yes, in principle, our algorithm can be very readily modified and applied to Wi-Fi, GNSS, satellite communication kind of platforms.
Thank you, Vignesh. I think there are a few things on the ML and the reinforcement learning. I think there is one comment and there is a question. How does the RL algorithm handle the disparate different inputs coming to the algorithms? Craig,
So yeah, I can take this question. So we would want our algorithm to be, working within the customer's ecosystem. So we can be kind of flexible about what's meant by the information provided from a certain sensor. So what I mean by this is, like, if you have, say, radar as an input, well, what exactly does that mean? Are you talking about, raw radar returns, or are you talking about a track that's formed, it's already been processed from the radar returns? Could we take that information in? So part of it is we can work with, say, something like a radar track or a process radar return, for example. And the disparate inputs, I mean, they're going to be sort of, the inputs are sort of all corralled in the ROS message system that passes information to our algorithm. So the way that we're handling these disparate inputs, it kind of depends upon the sensors available to us, how much processing went uh, into kind of shaping that sensor data, and then we can corral that into a message that can be sent to the algorithm.
Thank you, Craig. I think there is also a comment. I don't know who put that comment. I think the comment is about RL continuously adapts and improves spoofing detection capabilities, and AI learns the typical behavior of GPS signal in different environments and various under various conditions. This allows it to quickly identify deviation from unexpected patterns that will be indicative of spoofing. So I think we agree with this comment. So if you have any further input, we'll be happy to set up a call, and definitely we can discuss further about AI algorithm, how AI algorithm works. There's one more thing. I see you are trying to solve a similar level 5 autonomy for self-driving car. And as drone in the sky has limited compute power as compared to cars on the road, which may equip with high-end GPU for sensor processing. What are the challenges you see with level 5 autonomy for drones, and how Phoenix AI solve the challenges? Maybe I can take it. I think this is a really interesting questions. I think Craig has already covered, I think, some parts of it, but I can add more details. Just to make sure, I think everyone is aware. I think level 5 is a full autonomy without operator control. It could be for self-driving car, or it could be any vehicles flying, correct? It could be future in the sky. And I agree, I think AI models are complex and require substantial computational resources. The limited power and the computational capacity of drone can make these implementations model challenging, correct? Because I think for cars, yeah, I think on the road you could have high-end GPUs to process more inputs, and it's a different problems. And I think when we are in the sky, I think we have different sets of problems. So we're trying to solve a three-dimensional problems here, because drone can also fly not only X, Y, Y, but it could also fly in the Z. Like, so there are different directions that you need to look at it. Additionally, I think this models also requires, like, it has large volumes of training data, and which can be difficult to collect and process, correct? So we are aware of this limitation. So that is why we have developed, like, probably an innovative approach to solve these complex problems using the RL reinforcement learning models, which are trained offline, but only the Q table is put on the drone. And Qtable is optimized like compute power requirements of drones, and it requires like fraction of computational resources or capacity of the drone. So, basically, depending on, as Craig mentioned, depending on the use case, depending on the sensor input, we may have different compute requirements. I think that's one problem that we are trying to solve. The other problem, I believe, like, it's also important, is it's one of it's basically the challenge of the reliability and the predictability of these AI models, correct? Because AI models can sometimes produce unpredictable results on unexpected results, and this unpredictability could potentially lead to a safety issues in the sky. So ensuring the reliable and predictability of these models, the training models, is challenge. And so what we have done is basically we have developed an in-house simulation platform to recreate these real-world scenarios to train. So we can basically create continuous training. And as we get more training data, I think your AI model will be much predictive, much more efficient, much more accurate. So I think we covered most of the questions. So if you have any further questions, please reach out to one of us on this call. And don't know if you have any additional input. Naina, do you anything coming from your side? So again, thank you for joining us. I think for more info, please visit our website or contact us directly. I think we are trying to solve intelligent, like, important problem here. Happy to, yeah, connect with you offline. I think the drone anti-jamming technology is going to be crucial for safe and reliable operations uh, of drone across various sectors. And yeah, please reach out to us. So thank you all. Have a nice day.